Join us on Tomorrow's World Today as we journey through the worlds of inspiration, creation, innovation, and production to find the ideas and technologies that are shaping our future. In part 2 of this 4-part exploration, George sends Greg to discover the history of nuclear energy, how nuclear energy is being used in today's world, and what tomorrow's nuclear reactors might look like.
Hi everyone, I'm Greg Costantino. Now George has me on a very special assignment. I'm going to be looking at the past, present, and future of nuclear energy. Now we're going to start off by looking at the beginnings of nuclear research and the creation of fission. Next, we'll look at nuclear power today and safety, a topic on a lot of people's minds. And lastly, we're going to leap into the future, look at some of the innovations happening with this amazing technology, and also get a look at the advanced reactors of tomorrow. Now, I can't think of any better way to start this off than by talking to Don Miley. Now, Don is a legend in the nuclear world because of his encyclopedic knowledge of the industry. Let's go meet him now. Hey, Don.
Greg, welcome to Idaho National Lab.
Thanks for having me. I'm very excited to be here today.
We're excited to have you.
So, Don, here we are at EBR-1, the EBR-1 Museum. Tell me about that.
So, Experimental Breeder Reactor 1. This was the first reactor built at the National Reactor Testing Station. It was built by Argonne National Laboratory. First of 52 reactors built here in Idaho. And this was the first place in the world to make a usable amount of electricity from splitting atoms.
And that's really what we're here to learn about today. Tell me about fission.
So fission, splitting atoms, that is exactly what nuclear reactors do. We use atoms of uranium-235 that naturally occurring in nature. We mine those like most other elements. And uranium-235 has this wonderful ability that when struck by a neutron, it will split into 2 new atoms. And the energy that had bound that together as a cohesive atom, when you break that bond, a lot of that energy is released in the form of heat. And what makes this useful is as that atom is splitting into 2 new atoms, 2 to 3 neutrons are released, which will go on to strike more atoms of uranium-235, getting more heat for more neutrons and heat. So that's the chain reaction we talk about. And we harness that heat to turn water into steam. Steam turns a turbine, which turns a generator, just like a coal-fired power plant. But we're not physically burning anything, we're splitting atoms.
Right, which is keeping that carbon footprint small.
Exactly what we want to do, yeah.
Great, well I want to find out everything about everything that you do here, so how about a tour?
Might as well, you're in the right place. Greg, here we are in the control room for EBR-1. When this was operating, one operator sat right here and ran the reactor.
Wow, that's amazing. Now, Don, explain to me, what's it mean when a reactor goes critical?
Critical just means it's at full power, and that's what we want.
All right, well, let's take a look at a reactor.
Let's go.
So, Don, we're actually looking at the top of the reactor.
Correct. That is the reactor head, the lid, if you will. Beneath that lid would be the fuel rods, which we have in the display here. Very small diameter, 10 foot long, and only 8.5 inches of uranium-235 fuel. And that is something amazing about nuclear is energy density. The core at 8.5 inches tall, about that big around, generated a lot of heat. The primary coolant entered at 440 degrees Fahrenheit, flowed up the rods and out these holes at 600 degrees at 300 gallons a minute.
And that's how we get to the point where this reactor generated the first usable electricity.
That is right. Why don't we go look at the turbine?
Okay.
Let's go.
So, Don, is this the actual turbine that generated the electricity from EBR-1?
Yes, it is. This turbine is what they were spinning with the steam, which turned the generator. They made electricity, lighting 4 light bulbs on December 20th, 1951.
Now, I know you had bigger goals than just lighting up a few light bulbs. Is this also the generator that lit up the town of Arco?
It is not. Actually, that was at a reactor about a half mile away from here that was called Borax 3.
Okay, now I know that EBR-1 led you down the road to learn a lot of new safety protocols, and I'm very interested in that. So can we take a look?
Let's go take a look. Greg, here we have a replica of what the experimental breeder reactor 2 control room looked like.
So this is where you put all of the safety things that you learned doing EBR1 into practice.
That's right. Let me show you how. Greg, this is probably the best way to show the importance of the safety of EBR2 and how they achieved it. The reactor itself sat in a tank of 86,000 gallons of sodium coolant. Argonne in 1986 ran an experiment with EBR2 in which they had the reactor at full power. They disabled all safety systems, automatic safety systems, and they turned their primary pumps off. Nobody in the world thought that was a great idea with the reactor. In this case, what happened was without the coolant flowing, the static coolant, the temperature began to rise. So that rose to the surface, dissipated the heat, and fell to the bottom again. Convection currents formed. And at the same time, the fuel in EBR2 is a little different than our power plants today. This was metallic uranium instead of uranium oxide that the light water reactors use. Metallic fuel will begin to expand and neutrons leak out of the core and it shuts itself down. It is inherently safe in this design.
Well, Don, thank you very much. This has been excellent.
Thank you.
I'm heading out to Oak Ridge National Labs now.
Say hi to my friends there.
Will do. Now that we've learned about the history of nuclear energy, I'd like to dive a little bit more deeply into the safety of this technology. I'm going to meet with Dr. Rita Baron-Wall. She's with the Electric Power Research Institute, and we're going to talk about safety and also about nuclear power's contribution to today's energy mix. Hi, Rita.
Hi, Greg.
So, Rita, we've learned that nuclear energy is going to be a major part of the clean energy mix for the entire world moving forward. But people do have concerns, and they're generally about safety. Is it safe?
It's absolutely safe. But let me talk about the energy mix for a moment. Moving forward, the clean energy mix, studies have shown, are going to be about 80% renewables. The remaining 20% really needs to come from nuclear. Nuclear power plants follow the strictest and highest standard of safety, security, cybersecurity, and emergency preparedness. And nuclear power plants are designed such that they operate as remote islands, and so they are protected from cyber threats.
All right, well, there's a thing called value proposition as regards nuclear energy, and I want to find out a little bit more about that. So, Rita, when we talk about the value proposition of nuclear energy, what we're really talking about is the carbon footprint.
Nuclear has always been a clean energy source. It's really important in a clean energy mix when we talk about decarbonization. For example, in 2019, nuclear energy avoided 476 million metric tons of CO2 emissions. What that really equates to is the equivalent of taking 100 million cars off the road.
Wow.
Now, in terms of an actual footprint, a 1,000 megawatt nuclear power plant will require about 1 square mile of land area. Compare that to a windmill farm of an equivalent output. That'll require about 360 times the land mass. And a similar sized output from a solar photovoltaic plant is going to require about 75 times the land mass. While it's very important that we have all of those clean energy sources in a clean energy portfolio going forward, nuclear power plants require the smallest actual footprint.
Right, and in terms of reliability as well, I mean, wind and solar, they are great and amazing, and they're going to be a big part of this, but they are weather dependent.
Absolutely, and nuclear energy and nuclear power are a 24/7, 365 available energy source for electricity. And given our unfortunate climate events that we're seeing around the globe recently, it's really important to have nuclear energy as part of that mix so that you do have reliable and resilient power.
And that's part of the key too in what we're learning about energy poverty and getting power to places that either have no electricity or have very unreliable electricity.
And I talked about those larger 1,000 megawatt plants. The exciting part of this industry is that we're innovating and developing smaller reactors, including microreactors, which are 10 to 20 megawatts in size, and small modular reactors, which are up to 300 megawatts in size. Those can be deployed more rapidly to communities that either have no electricity, as you mentioned, or don't have reliable electricity much faster than a larger 1,000 megawatt scale plant could be deployed.
So this is a great way to get remote locations clean and reliable power.
Exactly.
So Rita, when it comes to nuclear energy, one of the main things that people are concerned about is nuclear waste. So tell me, what is it and how are we handling it?
Nuclear waste, or used nuclear fuel from a commercial power plant, actually goes into the reactor as a solid, and it also comes out of the reactor as a solid. After that, there's two different paths that can be pursued. One is to prepare that used fuel for permanent storage, and the other is to recycle that used fuel for reuse. And what's really exciting about advanced reactor designs is that some of those concepts are planning to use used fuel in their designs, thereby reducing the amount of used fuel that's really out there.
That's great. But now, when we talk about that permanent storage, how much are we talking about?
Well, for example, in the United States, since the 1950s, the amount of used fuel that's been generated is only enough to cover an American football field 10 yards deep.
That's amazing. Rita, this has been great. Thanks for all the great information. I'm heading over to Oak Ridge National Laboratory. I'm going to meet with Kathy McCarthy.
We're standing at Oak Ridge National Laboratory in the Visitors Center and actually in front of a mural that has highlights of all sorts of amazing things that have happened here. Oak Ridge National Laboratory has both the facilities and the expertise to solve some of the hardest problems that are facing humankind. Oak Ridge has a long history in nuclear science and technology and reactors specifically, over 7 decades of experience. In the work that we're doing currently, we're supporting both the current fleet of nuclear reactors. They provide over half of the carbon-free electricity generation in the United States. But we're also supporting advanced nuclear reactors. The U.S. ITER project office is located here at Oak Ridge National Laboratory. ITER is an experiment that's being built in southern France to demonstrate sustainable fusion energy, a step towards practical fusion energy.
Hi, Kathy.
Hey, Craig.
Now, Kathy, Oak Ridge National Laboratory has over 7 decades of experience in the nuclear power industry. That's a lot of history, but as I look around this room, I feel like I see the future of nuclear energy.
That's exactly right. What you see here is an example of the kind of modeling and simulation that we can do. We can do that because we have very powerful computers, and we also understand the nuclear science and technology that goes into the models that we're developing. These models can be used in a lot of different ways. One of the applications is we can use these models to look at if we make changes to a design, for example, what kind of benefit does that have on the economics? And that's an important part.
Right, and I guess that would also play into keeping the current nuclear fleet operating past its initial life expectancy. Tell me about that.
So the original licensing period for nuclear reactors is 40 years. That was based in the Atomic Energy Act on antitrust and depreciation laws. No, it was not a connection to the technical length of time that a reactor could operate. So there's the 40 years, and there's also a process for 20-year extensions to that 40 years. And for each of those extensions, the owner-operator needs to show that they can operate safely through these extended licensing periods.
So this was an economic concern, not a safety concern.
No, that's true, because what the plants have to demonstrate is they'll continue to operate safely, and that may require investments in replacing components and repairing components, and so in the end, it's that economic decision.
And as more technical innovations are made in reactor construction, there might come a point of diminishing returns on that upgrade.
That's absolutely right, and the other piece of that is with some of the advanced reactors under development, you can use them in a broader range of applications. So for example, in some of the reactors, they have a hotter outlet temperature. That means you can apply it in to different things, like, for example, in the chemical industry, where currently they use natural gas that produces greenhouse gases. If they want to reduce their carbon footprint, nuclear is a potential option. These reactors, some of them, give you this higher outlet temperature, which allows these other applications.
Right. Well, the chemistry thing kind of brings us to my next question, which is fission versus fusion.
So fission and fusion, they're both nuclear reactions. They involve the nucleus of the atoms. So if you think about your periodic table, and you've got the lighter ones up at the top down to the heavier ones, fission, you're actually breaking apart these heavy atoms that produces energy, what we call fission products, which are radioactive, and neutrons. In fusion, you're putting together lighter atoms, and so hydrogen isotopes, for example, you get energy, helium, and neutrons. So the difference really is the radioactivity of the fission products.
Okay, and that leads us to one of the most exciting developments in nuclear energy today. It's called ITER. I know that you have an ITER pellet lab here on site, and I'd really like to see it.
Great, I'd be happy to show it to you.
So, Kathy, this is the pellet smashing injector, which is by far my favorite name for a high-tech piece of scientific gear. And this is part of the safety protocol for ITER, and we'll get into that in just a minute. But first, tell me, what can we expect from ITER?
So ITER, which means the way in Latin, was designed and now is being assembled first and foremost so that we can understand the physics behind a self-sustained plasma, what we call a burning plasma. So you heat that plasma up, but then you don't want to have to keep having external heating. You want it to be self-sustaining.
Okay, so I know that plasma's really hot, and this is meant to cool it down. So explain to me how this works.
So the shattered pellet injector actually is used to dissipate the heat from the plasma. So ITER is first and foremost an experiment. And in an experiment, you have to be prepared for things not operating quite the way that they'll need to ultimately in a commercial plant. This is actually what the fuel pellet looks like in terms of size and shape. And the way that this test stand works, and this will be similar to how it works in ITER, we form the pellets here. And the way we do that is we've got liquid helium, so about 4 degrees Kelvin, which is minus 269 degrees centigrade. And we use a process called desublimation. So we're basically turning a gas into a solid, very, very cold. You can think about freezing. Mm-hmm. That's done in this section right here. Now in ITER, those pellets will be there in the system already ready to go.
Okay.
We use gas to push the pellet into this section. And we've got all of this instrumented with cameras so that we'll be able to see what happens, because how this pellet shatters is key to the experiment. In this section here and this section here, we're pulling the gas off that you used to push the pellet through, because all you want to go into the plasma is the pellet itself, because the gas will actually cause us to lose confinement of the plasma, and we don't want to do that. Then the pellet comes into this section, and this is what simulates the tokamak inside of the tokamak. Okay. And then we want to understand again how this pellet shatters so that we can make sure that it will uniformly dissipate the heat.
And I guess that's the same sort of theory as take a hot cup of tea and you drop an ice cube in it. It'll cool it down, but it takes a while. But if you dumped a bunch of crushed ice into it, it cools it down much more quickly.
That's right, and it's not just the much more quickly, it's also the uniformity of cooling. It's much better when you've got those different pieces.
Okay, now I know that just one of these injectors is not going to be enough to cool down that kind of a reaction. How many of these injectors will be positioned around the tokamak?
So ITER will have 27 shattered pellet injectors, 24 of them around the circumference and then 3 from up on top.
And exactly how will the cooling action take place?
So what happens is these shattered pellet injectors will fire basically simultaneously. They'll fire their pellets into the very hot plasma.
And how do you make sure that they all fire off at the same time?
So we can do that via sending an electronic signal. And the reason why we need to have it happen basically simultaneously is the plasma will cool very, very quickly. We're talking on the order of milliseconds.
Wow.
And you don't want one side to cool before the other side. You want to uniformly dissipate the heat. and it will dissipate quickly.
Okay, so we're going from really high temperatures to really low temperatures. What kind of temperatures are we actually talking about?
So think about the temperature of the center of the sun, which is 15 million degrees centigrade. The plasma is actually 10 times hotter than that.
That's 150 million degrees. How do you even know you can do that?
It's been done in laboratories already. Our challenge here is to do it for longer periods of time. That's one of the big challenges.
Okay, now when ITER goes online, which is around the mid-2020s, around 2025, what can we expect?
So in the mid-2020s, in what's called first plasma, that's where we'll demonstrate an integrated operation of these major systems. We've got superconducting magnets. We've got the system that keeps the superconducting magnets cold. We have this large vacuum vessel. All of this at plant scale. So first demonstrating that those systems all work in an integrated sense. Then we move towards full deuterium-tritium operations. This is the fueled portion of the ITER operations. And at that point, that's when we'll be able to demonstrate a self-sustained plasma or a burning plasma. And that will be in the mid-2030s.
Well, Kathy, this is super exciting stuff that we'll be sure to keep an eye on. Thank you very much. And thank all of you for being with us for our continuing exploration of nuclear energy. Now, in our next episode, we're going to look at more of this amazing technology and its role in tomorrow's world. For Tomorrow's World Today, I'm Greg Costantino.